And it's going to be Xiaoping Zhu from Rutgers, who is going to speak about the convergence of discrete uniformization factors on closed surfaces. So the floor is you, Xiaoping.
Okay, thanks for the invitation. Now I try to make this full screen. It's now a full screen mode?
Yes, it is full screen.
Okay, thanks for the invitation. Today we're going to talk about convergence of discrete uniformization factors on closed surfaces. This is a joint work with Riemann and Tianqi Wu. This has been covered in Hannes' talk, and two Riemannian metrics, conformal equivalent if there is a function on M, and they're related by scale factors. And the uniformization theorem tells us for a connected Riemann surface in a conformal class, there is always a complete metric has constant curvature. And if M is just a simply connected domain with Euclidean metric, then the uniformization theorem just implies the Riemann mapping theorem. And here comes the question, how to compute and discretize the Riemann mapping theorem, Riemann mapping and the smooth uniformization functions. Oh, sorry. Uniformization function U bar. Thurston proposed we can use some sort of circle packing to approximate. So circle packings are collections of closed disks with disjoint interiors, and its nerve is just like the red graph in our picture, the finite graph with vertex set in each interior of the disk and the edge between two vertices if a corresponding disk are tangent. And Koebe-Andreev-Thurston, they proved the theorem for any topological triangulation of a unit sphere, it can be realized as a nerve of circle packings of the unit sphere. On the left-hand side of the picture, we have a Delaunay triangulation, and the right-hand side it can be a nerve of circle packings of unit sphere. And as needs to be pointed out, this KT theorem also holds for the unit disk. So how to construct some sort of discrete conformal mapping to approximate Riemann mapping? So in the picture, we have a simply connected domain omega, and we have Riemann mapping F sending this omega onto the unit disk. And F sending some P to the origin, and we require the derivative to be larger than 0. And Pn will require on the right-hand side to be the maximum hexagonal circle packings of omega, and the disk of the radii of the disk is 1 over n. And we also require P is the center of the one disk. And the KT theorem for the unit disk tells us there exists one skeleton. There exists the circle packings of unit disk Qn such that it's isomorphic to Pn. And how do we define Fn? So for each center of, we're just sending each center of circle to the corresponding center, the center of the corresponding circle. And on the skeleton of the circle packing, we just do the piecewise linear extension. And we also need to normalize to make the image of P under Fn is just the origin. And Thurston conjectured that Fn converges to the Riemann mapping F. And this conjecture was proved by Rode and Sullivan in 1987. So the question now is, what about uniformization theorem for other non-planar cases? So this also uncovered we have marked surfaces where S is a compact surfaces and also connected, and V is a finite subset of S. And the PL metric, Euclidean or hyperbolic, define marked surfaces as V is a metric gluing of Euclidean or hyperbolic triangles by isometries along the edges so that its vertex set is just a V. And you can see that this metric is determined by the edge length function. And here is different from in Nanostalk. Here, the discrete curvature is just defined as the angle defect to be 2 pi minus sum of all inner angles at V. Also, that's Delaunay triangulation, which has been covered in Korean stock, that for an empty circle condition is satisfied. For any adjacent two triangles T and T prime, the vertices of T prime that not in the vertex side of T is always outside the interior of the circumscribed circle of triangle T. And here we talk about discrete conformal equivalence for PL metric. And here the definition is a little bit different from Heine because we have two kind of moves. So first is the same for PL metric P. We can also find a Delaunay triangulation such that realizes PL metric. And the first kind of move is, as in the picture here on the left-hand side, sometimes we do the flip operation. Replace T to be another Delaunay triangulation T prime, also realize our PL metric. And the second kind of move is just covered in Hanna's talk, is by a vertex scaling for the vertex function U. And also require the two triangulation, both of them are Delaunay. And here U star L means for Euclidean PL metric is related by this function, and for hyperbolic is related by sinh of length. And we say two PL metrics D and D prime on the marked surfaces SV are discrete conformal if they are related by a sequence of such two kind of moves. And Luo and his collaborators proved that for Euclidean metric on closed surfaces, and also we have prescribed curvature conditions satisfy the discrete Gauss-Bonnet formula. And there always exists Euclidean PL metric D star such that D star is in the discrete conformal class of D, and also the discrete curvature of D star realize K star. And they have the similar result for the PL hyperbolic metric. Here, discrete Gauss-Bonnet formula changes. That should be strictly larger than 2 pi Euler characteristics. And also for the theorem 1, this Euclidean PL metric is up to scaling, but for the hyperbolic PL metric, it's unique. In the above theorem for hyperbolic PL metric, if you imagine that all the discrete curvature to be 0, and that discrete hyperbolic PL metric becomes a hyperbolic metric on S. And I should mention that this case is first proved by Flastre. And we can imagine if we have a geodesic triangulation on closed Riemannian surface, and we can just construct a PL metric. Here I only talk about hyperbolic PL metric, and the length function is just inherited from the geodesic distance. And we can, under this construction, we can construct a hyperbolic PL metric, or for the hyperbolic flat PL metric. And similar to the question in the Riemann mapping setting, we want to ask how close is this discrete uniformization metric D star to the smooth uniformization metric. And it's difficult to directly make a comparison between D star and the uniformization metric. Instead, we deal with the discrete uniformization factor with the uniformization function restricted on the vertex set. Similar to the Delaunay triangulation, we define a geodesic epsilon regular geodesic triangulation if the minimum of angle is always larger than epsilon. And also we require for any edges, the sum of the angle opposite to it is strictly less than pi minus epsilon. And this is joint work with Tianqi Wu. We prove that if we have a closed Riemannian surface Mg of genus larger than 1, and epsilon is a constant between 0 and pi over 3, and there exists a delta that will, depending on the Riemannian metric and also epsilon, such that if any epsilon regular geodesic triangulation with the maximum length less than delta, then there exists a unique U, we call it discrete uniformization factor, such that after the vertex scaling, the TU star L has 0 discrete curvature. And also, the difference between U and the smooth uniformization function U bar on the vertex set is controlled by the maximum length of our triangulation. And also collaborated with Yanwen Luo and Tianqi Wu, we prove similar results also hold for the genus 0 surface. But here we require the mapping fixed 3 points. And so this the following picture shows us how to define such a kind of approximation. So we have a Riemannian manifold Mg, and we have some sort of triangulation, epsilon regular triangulation, such that Ln is very small. And we know in our theorem, it's discrete uniformized to some for the genus larger than 1 case, is discrete uniformized to a hyperbolic metric. And this EU defined on the vertex set is very close to U bar. But we do not provide any algorithm. Okay, thank you.
Thank you.
And just run out of time.
Yep, just exactly on time. Impressive. So, but we do, because we only start the talk, the longer talk in the afternoon in some 15 minutes, we do have time for a few questions for Xiaoping.
How can I go back to the video?
To which video? You mean?
To the Zoom.
On the top screen.
Okay.
You should see something quit. Don't you see a green bar on the top?
Uh-huh.
And next to it, stop screen sharing.
Uh-huh.
Then do that. Just do stop screen sharing.
Okay.
Okay. You see, it works. Any question for Xiaoping? I'll start with a question. You mentioned it at the end in your last slide, but I'm going to poke you a little bit on that. Any algorithm for building?
No algorithm.
Why would it involve to build an algorithm now? I mean, you have an existence proof, but how do you go about constructing it?
So first we started with so discrete conformal is close to the smooth conformal when the length is very small. And so first we started with this U bar, the smooth uniformization function, and we make a flow from this smooth uniformization function to the desired result. So that's why we cannot provide an algorithm.
Let me say something. Yeah, I think the construction of the discrete uniformization conformal factor has already been well developed. And since we know it's just the critical point of a variational energy function, which is convex, And basically, there's very nice Newton's method could be used to compute that. And but our main contribution is prove the convergence. It is to prove that this discrete uniformization conformal factor is indeed close to the true continuous uniformization conformal factor. So the main purpose of our result is not to construct a discrete uniformization factor. That one is already well known to the experts, I think.
It's well known, but the reason I was mentioning it is the problem is they are just like Keenan had mentioned this morning. In many of the computational geometry implementation, you encounter numerical problems, and even though the energy is convex, you cannot guarantee always that you'll be able to rebuild your point. You're building the metric, but that doesn't mean you have the Euclidean realization of the metric.
But actually, the hyperbolic metric does not exist in real world. It's not in the 3 dimensionals, the hyperbolic metric. So I think maybe the piecewise flat metric may be more useful.
Sorry, maybe I did not follow well. We can rebuild the piecewise metric. More precise, we can construct the edge length function.
Yes.
And but certainly we cannot embed this surface into R3 because it's hyperbolic surface.
Yes.
Yeah.
But can you? Will it work for genus 0 surfaces?
Yeah, for genus 0 surface, we can reconstruct the edge length, and we can embed it into R3 because in this case, can we? That's another question. You know the intrinsic metric of the intrinsic PL metric of a spherical surface. How can you embed it into R3? Yeah, we did not cover that, but maybe. Yeah, I know Professor Bobenko has a work with its massive. They do have an algorithm to embed a convex spherical surface into R3 as a convex embedding.
But it works only in the convex case, of course, yeah?
Yeah, on the convex. Yeah, but for the spherical case, the discrete uniformization must be a convex, intrinsic convex surface. So it satisfies the assumptions there.
Well, it depends on your initial surface. You uniformize. You can start with, okay, total curvature is of course positive, but it may have pieces where the curvature is negative.
Yeah, but after the discrete uniformization, the curvatures are always positive.
Yeah, that's right.
Yeah, so there are 2 stages. Our stage is to construct the intrinsic PL metric. And
but which surface are you going to construct in R3?
The
round sphere?
It's isometric.
It would be a convex polyhedron inscribed in a unit sphere. Yeah.
Which is conformally equivalent to the original surface?
Yeah, which is discrete conformal to the original surface. Yeah.
Okay, that's what you can do, of course, yeah, because the metric is convex.
Yeah. So, Patrice, I'm not sure did I answer your question? Are you asking?
I think so. I think I see it in the case of the genus 0, and I see why it doesn't really work in the case of other genus. No, you did answer my question.
Thank you.
Any other question? So if we don't have any other question, I think we should end these short talk sections by thanking again Hannah, Hassan, and Xiaoping for the very interesting presentations they gave us. And we do have a sort of 5 minutes